Hey everyone, thank you for coming out tonight on this cloudy evening in the August version of Astronomy. Unfortunately, due to the clouds, we probably won't do any observing tonight, but again, hope for next month. In any case, we have a wonderful speaker, Dr. Stephen Giacalone, who's again another very bittersweet speaker, as Stephen has been running Astronomy here since 2019. We are fortunately sad to see him leave after tonight, but that won't make his talk any worse. Anyway, Dr. Stephen is a former graduate student here and is now a NSF postdoctoral fellow at Caltech. Again, we're sad to lose him, but Ace, enjoy.
Thank you for the introduction. Yeah, it'll be sad to leave here. You know, I've been here for 6 years. Moving down to LA to start my postdoc in just a few weeks now. So I'll sort of say my last goodbyes to Astronomy, but also everyone in my department before I go. But on a happier, more cool science note, we're going to talk about rocky planets tonight. And so most people familiar with rocky planets are, we're going to talk about what we know about rocky planets, what we're currently learning about them, and what we're going to learn in the future. And I think another thing that I want people to take away from this talk is just how broad of a scientific expertise we need to have in order to understand planets, not just in the solar system, but throughout the galaxy. So of course, you need to know the astronomy and the astrophysics. That's what our department is. But you also need to know atmospheric chemistry, you need to know geology, you need to know biology to understand what kind of life could exist on another planet and what signatures that life might create that we can detect. And so we'll start locally. So everyone knows what these are, right? For planets, Mercury, Venus, Earth, that's the one we're like, right? Did I pick the right planet? Oh, no, that's Africa. My bad. And Mars. So the immediate thing when I see all 4 of these planets, these are the 4 planets closest to the sun, of course, is that they're all very different, right? Mercury, almost no atmosphere, very rocky, very rich in iron, about 75% iron almost, a huge iron core. Venus has this big CO2 atmosphere that underwent this runaway greenhouse gas effect. Not habitable at all. Then you have Earth, almost exactly the same size as Venus, receives about half as much light from the sun, and it's perfectly habitable, and we live here, and we're very happy living here, hopefully for a long time. And then you have Mars, a little bit smaller, a little bit less massive, might have been habitable at one point, but we're not really sure. And it has this very sort of signature red surface. And so the thing that I really marvel over here is that all of these rocky planets are completely different. They're all around the same star, very close to it, and yet they all look completely different. They all have different atmospheres. They all have different surface compositions. So how do you get from a disk that planets form in and get so different, diverse outcomes? And so we're not just going to stop at the inner solar system. We're going to have a pop quiz now. So there are lots of rocky objects in the solar system, most of which that don't qualify as planets, unfortunately. But that all are very interesting in their own right. So people can shout out. People know what these ones are? Yeah. So yeah, that's Io. Europa. Ganymede. Yeah. Okay. So good job. So these are the Galilean satellites of Jupiter. So these are the ones that Galileo found with his telescope hundreds of years ago, orbiting around Jupiter, just like the planets orbit around the sun. But it doesn't stop there. So we're going to do a few more here, and they're going to get progressively harder, I think. Does anyone know what this one is?
Saturn's the Titan.
There's debate. Yeah, so that's Pluto. Good guess though, with the other ones. So I know this one's Pluto because it has the heart here. So this is from the New Horizons mission that actually did a flyby of Pluto only a few years ago. And it has this cute little heart. I think they released this on like Valentine's Day or something. So that was fun. So that's Pluto. What about this one? Yeah. So this is Titan. One of my favorite moons. It's one of the only other bodies in the solar system that is rocky that has a pretty thick, stable atmosphere. So unlike the atmosphere of the Earth, it's very rich in nitrogen, very rich in methane. And so it has the components for life to exist, but we can't breathe if we were to go there. And then this is the last one. I think this is the hardest. Yeah, okay. So someone got it right away. So this is Ceres. Do people know where Ceres is in the solar system? Yeah.
It's in the asteroid belt.
Yes, exactly. So Ceres is in the asteroid belt, so between Mars and Jupiter. Ceres was discovered in, I think, 1801. I find it very interesting because it used to be classified as a planet before the IAU sort of wrote its definition. People don't really talk about it. Everyone's upset about Pluto being demoted to a dwarf planet, but not Ceres. Or a minor planet, rather, sorry. But not Ceres. But I think that Ceres should get more attention. It's really interesting.
But it's not a moon then.
What was that?
It's not a moon.
Oh, it's not a moon, yeah. So I misspoke if I said these were all moons. So yeah, Ceres is technically an asteroid or a minor planet. I think it sort of depends on your definition. Okay. So the point of that whole thing was to say that what does a typical rocky planet or moon look like? All of these look incredibly different. I'm actually gonna go back for a second. All of these look incredibly different, right? These are all actual like visible light images taken of these bodies from missions that NASA and the European Space Agency have sent out into the solar system. And so the question that I want to ask is, what does a typical rocky planet look like? Is there a typical rocky planet? So in this talk, I'm going to sort of go through three topics here. The first one being, what is a rocky planet, right? I think there's obviously this debate over like what qualifies as a planet. And so it's reasonable to also ask, where do you draw the line at what is a rocky planet versus what is a gaseous planet? Can you get a planet that is the size of Neptune, but instead of having a really big atmosphere, is just pure rock and is just giant and has this incredible surface gravity? Before we studied exoplanets, we didn't know the answer to that, but as I'll show you, we sort of have an answer now. The next question I'll go into is, what kind of atmospheres do rocky planets have? So as we saw, there's an incredible diversity, even in the solar system, of the types of atmospheres that these rocky bodies have. So there's Earth, Venus, Titan, but there's also a lot of rocky bodies that don't have atmospheres at all. So is it the case that most rocky bodies, planets in the galaxy, in the universe, don't have atmospheres at all? That's something that we're actually getting closer to answering to today with JWST. And then the last thing we want to talk about, and this is out in the far future, is how common are habitable Earth twins. So if you took a sun-like star and you took a rocky planet roughly the size of the Earth, put it 1 AU away from it, which is the distance between the Earth and the sun, is that thing habitable always, or what fraction of the time are those planets habitable? So that's something we'll learn in the future, and I'll talk to you about at the end. Yeah.
Habitable by us?
Good question. So that's something that I'll touch upon. Yeah, the word habitable itself is sort of, Pandora's box. It's habitable to us, habitable to who? I think there's a lot of definitions that we can come up with there. Okay. So the first thing I need to go over is how we're finding these exoplanets. So the most common way of discovery of exoplanet is called the transit method. So for the transit method, you look at a whole bunch of stars, and if that star has a planet around it, and that planet is aligned just perfectly, it's going to pass in front of the star along our line of sight. And when it does that, it creates these periodic dips in brightness. So it's obscuring part of the stellar surface, and so it gets fainter. We get these very signature features that we call transits. And what do we learn from transits? So the first thing we know is the orbital period. So these are periodic dips. So, the time between one dip to the next dip is the orbital period. The orbital period of the Earth is a year. So that's what the analogous quantity is here. The other thing that you can learn is the semi-major axis. So if you know the mass of the star, use Kepler's third law to learn how far away the planet is from the star. You also know the stellar irradiation, so the amount of light the planet is getting from the star, because you know what the luminosity of the star is. and that's just from stellar physics, that's not from this method. And the last thing that you can learn is the planet radius, and this is the most important quantity in this talk. So you get the planet radius based off the depth of this transit. And so what you actually get here is the ratio of the planet size to the star size, and then you know the size of the star, so you get the size of the planet. So this method has by far discovered the most exoplanets to date. We have over 5,000 exoplanets today, and over half of them have been discovered by one of these two telescopes. So this is the Kepler Space Telescope. This was running for almost a decade. It discovered over 2,000 exoplanets via the transit method. That was retired in 2018, but luckily, right around that time, its successor, the Transiting Exoplanet Survey Satellite, started up. And this is different from Kepler in that it's looking for planets around stars that are much brighter and a lot closer, so they're going to be easier to study. Okay. Oh, and another important point. Most of the planets discovered by these telescopes and via the transit method in general have very short orbital periods. So when I say short orbital periods, I mean that they're closer to their stars than Mercury is to the sun. So they're really hot, they're going around their stars very frequently. And the reason for that is just because if you randomly orient an orbit in space, it's more likely going to be transit if it's closer, the planet is closer to the star. Okay. So we have the planet's size, or its radius. The next thing we want to know is the mass of the planet. And the reason we want to know the mass of the planet is because you can't really tell if something is rocky just based off its size alone. In principle, you can have something the size of the Earth, but that is just a ball of hydrogen. Or you can have something the size of Jupiter, and that is, pure rock. A priori, you don't really know which one of those things it's going to be just based off its size. So you need to know how much material is actually being packed into that size. And before I just talk about how we measure the masses, we need to do like a little recap of spectra, or it's not really going to make sense. So going back to our sort of high school physics classes, light is composed of photons, which can have discrete wavelengths. If you take light of all wavelengths, you get the electromagnetic spectrum. So the visible light is right here, and then if you go to longer wavelengths than red, you get to infrared, microwave, radio. You go to shorter wavelengths than violet, you get ultraviolet, X-ray, and gamma ray. So anything with a non-zero temperature emits a signature spectrum. It's called a black body spectrum, where it essentially has light of all different wavelengths in it in a certain distribution. And so the light source we're going to talk about here is a star. And so a star emits a characteristic spectrum. And it turns out that some of the light emitted from that star is absorbed by gas in the stellar atmosphere. And when it does that, it creates these dips here. So if you were to take the light from a star and spread it out into a rainbow, you would see that some parts of the rainbow have these black bands. And that's because the light is being absorbed and it cannot escape. These are called absorption features, and they're really important for a reason that I'll explain in the next slide. So you take this concept and you put it together with the idea of gravity. And so as a planet orbits around its star, the planet is tugging and pulling on the star, so the star is wobbling along our line of sight, which causes the spectrum to wobble back and forth due to the Doppler effect. It's being Doppler shifted to the red here, and then Doppler shifted to the blue when the star is going the other way. And we can take those shifts and turn them into velocities, and then create a plot like this. So this is radial velocity. This is how fast the star is moving towards away from us versus time. And you'll see this wiggle. And you can extract some interesting information from this wiggle. So like before, you can get the orbital period, semi-major axis, and the irradiance on the planet, but you also get the planet mass. So for all these planets that we're discovering via the transit method, we're also trying to measure the masses via the radial velocity method to get both the radius and the mass. And so what we can do from there is use interior models of planets to try to figure out how big a planet can be when you take a given substance. Okay, I'm going to start over there because I messed that up. So we take interior models. If you know the mass and the radius, you know the density, right? So you can take different compositions. So you can take rock, you can take ice, whatever you want, and you can take a model that compresses a certain amount of mass with gravity, and then figure out how big it's going to be, essentially. And so this is what exoplanet scientists have done. And so these lines here are what we call isocomposition lines. The lower line is if you took something that is pure iron and you compressed it into a ball. The middle line is if you had something that is Earth-like composition and compressed it into a ball. And the top line here is if you took something that is pure water ice and compressed it into a ball. How big it's going to be for a given mass. And so all the points plotted here are exoplanets that we've discovered and have measured the sizes and masses for. And we can start to see at what point in radius are things no longer lying along this Earth-like composition line. So you see that everything roughly smaller than 2 Earth radius is roughly Earth-like in composition, but as soon as you get bigger than about 2, things start to blow up here. So that they no longer lie along these lines. And what that's indicative of is that they have to have volatile rich atmospheres. So they have to have atmospheres of hydrogen and helium, much like Uranus and Neptune and Saturn and Jupiter, which are up here. And so we learned something with these methods, which is the answer to our first question, and that is that nearly all rocky planets are less than about twice the size of Earth. And so we have our first result. What is a rocky planet? It's something that's probably less than twice the size of Earth. And I'll pause here for questions because I saw this as a hand raise.
Sorry, when do you use emission spectra or absorption spectra? Because sometimes I feel like the absorption spectra, the emission spectra would fill in the lines of the absorption spectra, right?
So you mean for like this part here?
Yeah.
So for stars, you're mostly seeing just absorption spectra, but I am going to get to emission spectra in just a minute. Yeah. So okay, reiterate, pretty much all rocky planets out there in the galaxy are less than twice the size of Earth. Yeah, go ahead.
Okay, yeah, so wouldn't the wobbling of the star have to be a significant fraction of the speed of light before you saw any Doppler shift in terms of the spectrum? I mean, how is the tiny wobble enough for you to actually be able to see anything?
Yeah, that's a good question. And I think the answer is that it is a very tiny wobble. If you were to take aliens that were looking at the solar system and tried to measure the wobble of the Earth on the sun, the wobble of the sun due to the Earth orbiting around it, it would be roughly 10 centimeters per second, which is the speed of a snail, essentially, or a turtle.
So that gift that you showed was highly exaggerated.
And that was highly exaggerated. But we can actually measure things down to about a meter per second.
What per second?
A meter per second.
Wow.
And we're making spectrographs that are even stronger on bigger and bigger telescopes that are pushing the limit and getting down to close to 10 meters per second.
So how much would that would like barely move, like if you actually blew that up to like make the spectrum of those lines, would barely move like a micrometer.
Yeah.
Or such.
Exactly. So instrumentalists, physicists have to get really clever with how they design their instruments to detect these really, really tiny Doppler shifts, but they are able to do it. It's pretty incredible how precise we're able to measure these things. We're actually down to the point where the limitation is not really our ability to detect that shift. It's more that stars themselves have intrinsic noise, like stars are pulsating.
Yeah, I almost feel like that would be stronger than the tiny planet.
Yeah, well, no, exactly. So for some planets, very small planets, that stellar noise creates shift in radial velocity that are larger than the signal due to the planet. And so people are trying to come up with ways to what they call like stellar activity suppression to correct for those stellar signals so that you can back out the planet signal that's underneath it. Yeah, a lot of very like challenging technical problems that these instrumentalists have to tackle. But it's really interesting. So yeah, if people are interested in that, I'm happy to talk about it more afterwards. Okay. So that was number one. Now I'm going to get into JWST. I can't say that for some reason. So JWST is a new space telescope that was launched just a few years ago. It's currently taking data. Results have already been released, and I'll show them in a couple minutes. So this is a mission that looks, it has a bunch of spectrographs essentially, and it looks in the infrared. And because it does that, it's able to access the atmospheres of planets. It's able to tell what's in the atmospheres of planets. And it does that via two methods. So the first method is called transmission spectroscopy. And I'll go over each of these methods. So here we have a star, we have our observer here. So imagine this is JWST. We have a planet that I chose. It's pink on my screen, but it's like purple there. Either way. So the planet's going around the star. It eventually reaches a point where it's in the middle of transit, so it's blocking this, partially the star. And we'll zoom in here. And so we have our planet, and we have light rays of different wavelengths. So we'll have some red lights and green lights and blue light, because the star is emitting light across its whole spectrum. And it eventually reaches the atmosphere of the planet, and it tries to go through it. But atmospheres have things called molecules. That can be water, that could be CO2, that could be methane, etc. That sometimes absorbs the light that is coming from the star. And so some light, like in this case, the green light, is not actually going to be able to get through the atmosphere of this planet. And so we'll only see the red and the blue light. So that's a very simplified cartoon here. But this is what some actual data would look like if you looked at the atmosphere of, in this case, a giant planet. So on the y-axis here, you have the intensity. So this is how much light is getting through. And on the x-axis, you have the wavelength of the light. And so you see that we have these dips here and these peaks here. And this is due to light being absorbed by, in this case, water, carbon monoxide, carbon dioxide, etc. And so if there were nothing in the atmosphere of this planet, it would essentially be flat. But because we see these wiggles, we can infer that there's things like water in there.
How can you distinguish it from, like a solution from the star?
Oh, so what people do in practice is, I'll actually go back to this. So when they're taking these observations, so I'll reiterate, the question was, how do you discern these dips in the planet atmosphere from those of the star's atmosphere? And so what people will do is they'll actually start taking data like now, so pre-transit, and then they'll continue to take data as it's in transit. And then you literally just like subtract the in transit from the out of transit, and then you remove all the stellar lines. That's a good question. Okay, let's go back forward. Okay, so that was transmission spectroscopy. Next is emission spectroscopy. So this one's different. We don't look for the gases in the planet atmosphere while it's transiting. We instead wait for the planet to loop all the way around and be almost behind the star. So we'll zoom in again here, what this looks like. And now we have to take into account the fact that only part of the planet is being illuminated. So we have a hot day side over here. This is the part of the planet that's being illuminated by the star. We have a cold night side over here. And on the hot day side, it's actually hot enough that the planet itself is emitting light that we can detect with our detectors. So there's light coming out from this interior of the planet here. And again, there are molecules in the atmosphere of the planet. So some of the light that's being emitted is not going to make it out. And so green light is absorbed again, and the red and blue light gets through. And this is what an atmosphere might look like through emission spectroscopy. And so again, we see these peaks here, which is regions of very, very large emission from the planet. And then we have these troughs, which is where light is being absorbed.
So this isn't reflected starlight you're talking about. This is actual thermal emission from the planet itself.
Exactly. So this is thermal emission.
Okay.
So the reason why JWST is good at thermal emission particularly is because it looks so far in the infrared. If you were looking in the optical, so if we were to look in at the color red that we see, there is a big degeneracy between reflected light and thermally emitted light. But as you go farther and farther into the infrared, that reflected component really diminishes, and you really get mostly emission. Yeah, go ahead.
Well, what sort of planets can you observe through this method? Because I feel like there would only be maybe brown dwarfs that are large and have energy.
Yeah, that's a great question. So the easiest atmospheres to characterize are giant planets and brown dwarfs. So you're correct. But in some very specific instances, which I'll go to on the next slide, you can actually get down to like rocky planet-sized things. I like all your questions because they lead into like the next slides. Okay, so transmission and emission spectroscopy, that's what JWST is doing to characterize the atmospheres of these planets. So now I'm going to go into like a sort of case study, and that is going to revolve around the TRAPPIST-1 system. So show of hands, who here has heard of TRAPPIST-1? Okay, pretty good. So almost half the room. So TRAPPIST-1, for the people that don't know about it, is a nearby M dwarf. So M dwarfs are stars that are about half as hot as the sun and less. So TRAPPIST-1, which little sliver here is the star, is about 2,500 Kelvin, whereas the sun is almost 6,000 Kelvin. So it's less than half the temperature of the surface of the sun. And so people were looking at the star and they found a transiting planet. First, they found B, which is the closest one to the star. And they said, okay, that's interesting. This is an important star because it's very close. It's relatively bright for an M dwarf. So we want to keep looking at it, see if we recover more transits and find more planets. And they kept looking and they kept looking, and then they found 6 more planets. So this is one of very few systems that we know of that has many transiting close-in planets. And the interesting thing about the system is that because the star is so cool, the planets actually receive about as much light as the planets in the solar system do from the sun. So the closest planet B receives about 4.25 times Earth's irradiation. Planet C is about twice, so this is almost equivalent to Venus. So Venus receives about twice as much light from the sun as Earth does. This planet receives about twice as much light from its star as Earth does from the sun. D, E, and F, and G are all interesting because they're all roughly where you need to be for water to be in its liquid form. I think he's a little bit too hot. People don't really consider that. But these 3 here, people consider to be within the habitable zone. So again, that word habitable, I'll put like air quotes around. When astronomers say habitable zone, they're essentially saying the distance from a star or planet needs to be for water to be liquid, rather than frozen or in its vapor form. And then H is also cool, but people don't talk about it as much. It's relatively cold. So this is a really cool system. It's a really great case study to look at how the compositions and atmospheres of rocky planets change across this whole spectrum of very irradiated to not irradiated very much at all. And it enables us to really make a strong comparison to the rocky planets of the solar system. So these are all being observed by JWST. But these 2 actually results come out within the past couple months. So I'm going to talk about the results of these 2 inner planets. So I'll say quickly, these 2 planets were observed via emission spectroscopy. So they're closest to the star, which means that they're also very hot. The day sides of the planets are very hot. And so we can detect the emission from them very easily. Now I'll start with B. So these are results from Tom Green, who's at NASA Ames, just down in the South Bay. He was one of the designers of one of the instruments in JWST. So we got to write this paper that looks at the atmosphere of TRAPPIST-1b. And so what they did is they measured the amount of light coming from the day side of the planet, and they compared it to models of what you would expect to see for a Venus-like atmosphere. So these lines down here correspond to about 100 bar CO2 atmospheres, and about 10 bar CO2 atmospheres. Venus's atmosphere is almost entirely carbon dioxide, it's about 100 bars. So this is essentially a Venus atmosphere. And then these lines up here are what you get if you had essentially a black body. So if you just had a rocky surface, there's no atmosphere absorbing things, you just have light bouncing off rock and into our telescopes. So what they found is this up here. And so very much consistent with essentially a rocky surface. They didn't detect any carbon dioxide in significant amounts in the atmosphere of this planet. And so this is really the first indication that rocky planets very close to their stars, even if they receive roughly the same amount of irradiation as Venus, for example, might not have atmospheres at all. Okay, so that was B, but what about C? So C's a little bit farther away, receives about half as much light as B does, and so maybe it has a better chance of having an atmosphere than B. So these are results from Sebastian Ziba, who is a graduate student over in Europe. And he found a pretty similar result. So again, he got these emission data points. This is the line you would expect for a Venus-like carbon dioxide-rich atmosphere. This is a line you would get for a carbon dioxide-rich but very, very low pressure atmosphere. So something much less abundant in molecules than even like Earth is. And then this is the line you would get if you just had a ultramafic rock surface that the light is bouncing off of. So again, they found essentially no thick Venus-like atmosphere, most likely a bare rock. And so that's a little bit disappointing, but it's also interesting, I think. We're starting to get this indication that there are probably a lot of rocky planets out there that don't have atmospheres, even if they're roughly the same size as Earth and Venus. So these remaining 5 planets are either currently being observed by JWST or are going to be observed in the future. These are actually a little bit too cold to do emission spectroscopy, so they're doing transmission spectroscopy with these. So these planets are transiting in front of the stars, and they're going to look for the atmospheric signatures in that way. Yeah, go ahead.
Are these all rocky planets?
Yeah, I forgot to mention, I should have put it up here. These are all roughly the same size as the Earth. So
Are there any gas planets around this star or?
not as far as we know. Yeah, go ahead.
Wait, sorry, for TRAPPIST 1C, it was completely no atmosphere, or there was a very thin carbon dioxide atmosphere?
So, yeah, good question. We can never really rule out the presence of an atmosphere at all. So yeah, their data point here is consistent with a CO2 atmosphere and an O2 atmosphere that's only 0.1 bar. So the Earth's atmosphere is about 1 bar at the surface. So this could in principle have an atmosphere that is only like a 10th as massive as the Earth's.
Could be anything like Mars, kind of?
Yeah. So more similar to Mars or even Mercury. Like Mercury technically has an atmosphere, but it's like so thin and unmassive that I don't know. It's not very interesting. Lots of questions. Yeah, in the front first.
Yeah, so are they only measuring at like a single wavelength here?
Yeah,
Is that just because they had to only do one at a time?
good
Or
question.
why aren't we looking at the line? Why do we just have a point?
Good question. So it is possible with this instrument to do like a full spectrum from here to here. They wanted to choose this point specifically because they knew that this big CO2 feature is right here. And so this gets into the weeds a little bit with like efficiency of JWST observations. If you just want to do one wavelength bin here, you can get that data with a lot less time than if you wanted to get high signal to noise data across this full range. And so for the people proposing for this for these observations, they essentially said like, well, we can go for like a little proposal that's probably more likely to get accepted. Just looking for this one, whereas if we propose for like a bigger proposal to do this full range, they would have to come up with like a really good justification for it. And so that's just a little like insider baseball, I guess. But yeah, go ahead.
So that's photometry.
So yeah, this is photometry. I was saying spectra. This is technically photometry, but people are going to keep getting observations in different filters, so like over here and over here. So it's sort of like a spectrum at the end of the day.
And so the other planets that are planning to observe maybe takes longer because they have less radiation.
Yeah. Yeah. So yeah, if they wanted to do the emission observations like this, they would require a lot more data. So right now, what they're doing is they're trying to do that transmission spectroscopy. So they're observing transits, which is a lot harder because these atmospheres, if there are any, are very, very thin. Yeah, go ahead in the back.
So how large are these planets with relation to the Earth? Because I think that, if the star was smaller, then surely the accretion disk would also be smaller, and therefore the planets would also be smaller.
Yeah, that's exactly right. So yeah, these are all roughly Earth-sized planets. And yeah, there is evidence that these M-type stars, so these very low mass, cool stars, cannot form giant planets as efficiently as sun-like stars, for example. And so we know this is actually work that my advisor did. I don't have a slide in here for it, probably should. My advisor used the Kepler Space Telescope to look at the occurrence rate of small rocky planets around M-type stars. So occurrence rate is a fancy word for saying how likely is any given M-type star to have a rocky planet. And what she found is that like pretty much all of them have rocky planets. So they're very abundant. Also, M-type stars are very abundant. They're like 70% of all stars in the galaxy. And so these rocky planets are essentially ubiquitous, right? Which is another reason why this is really interesting, right? If we want to know what the true fraction of like stars that have habitable planets is in the galaxy, we really need to know the answer for these M-type stars because, yeah, most of the planets in the habitable zone in the galaxy are going to be like this. Yeah, go ahead.
I know water is absolutely essential for life on Earth and it like, you know, is universal, like it's a good solvent, etc. But why, like, do you think there's any limitations to like emphasizing research just into regions where water would be liquid and like missing out on like other molecules being liquid and being essential for life?
Yeah, I think you make a really good point. So as far as exoplanets go, I think we're really just limited in our how much information we can actually get out of the data right now. So water is a particularly easy thing to go after. It has a lot of absorption features in the infrared. And so yeah, it's sort of like the easy thing to go to. But I think we're going to find out in the next few decades, not with exoplanets, but with missions within the solar system, they're going to go to like Titan. They're going to go to the oceans of like Europa. I know it's still water, but we're going to be able to look for, can life arise in environments but there's not a lot of water, but there's liquids of other molecules that could potentially serve as that sort of primordial soup, whatever they call it, of where life first started. Yeah, go ahead.
Again, you're not extrapolating just from this very tiny sample set, right? I thought you heard something about, well, most of these rocky planets, they're going to be like this. We have no idea, right?
Yeah.
Because even in our own solar system, 2 of the 4 have hardly any atmospheres, 2 do. So
yeah.
Oh, okay.
Yeah, no, that's a great point. Yeah. So yeah, extrapolating from any one data point, so any one star, is never a good idea. But there are a lot of other rocky planets around M-type stars and around hotter stars that people are looking at or are proposing to look at with JWST. So the goal, the really overall goal of JWST was to build that statistical sample of planets of all different sizes around different types of stars to look for those trends and like what types of planets have atmospheres, what type of stuff is in the atmospheres of this type of planet versus that type of planet, and really reach like a statistical level. So these case studies are important and are interesting, but they're only a tiny piece of the puzzle that we're going to, I guess, finish assembling within the next decade or 2. Yeah, go ahead.
Are there any other stars that are currently in the planning phase of us planning to look at with JWST?
Oh yeah, there's a lot. I could name a few, but I don't think it would like make that much sense. There's interesting ones, and I'll get after these slides. I'll get into like other interesting planets that like definitely aren't habitable, but we're able to do other cool physics with. So yeah, I'll go on to those now. So those are M dwarfs. But there are also other types of stars, right? Stars like the sun are hotter than M dwarfs, and those sometimes also have rocky planets around them that we can observe with JWST. And so, what's the deal with those planets? What can we learn from them? They're probably too hot to have liquid water, but there might be something else interesting going on. And that interesting thing, this is something that I'm pretty heavily invested in, is lava worlds. So, yeah. So what is a lava world? I think that when people say the word lava world, people automatically put on their like skeptical hats. And they're like, well, you don't know if it's really lava. I was listening to a podcast once, and they were like, these astronomers say that there's lava worlds. They don't know. And I think I convinced you pretty quickly that we do know. So what is a lava world? So a lava world is a planet where partially or fully molten day sides due to really intense stellar irradiation. So we know that silicate rock, so the rock that the Earth is made out of, starts to melt at about 800 Kelvin, so that temperature of about 800 Kelvin. And we've discovered rocky planets around sun-like stars with day-side temperatures of over 2000 Kelvin. So there are, I could say, unless they have like a really weirdly extremely reflective surface and they're not absorbing any heat from the star, which I don't even know what that would be, there are definitely lava worlds, and there are lava worlds that we can observe with JWST. And one of the interesting things about these lava worlds is that they should have outgassed atmospheres that are composed of vaporized rock. So these are atmospheres, unlike Venus's or Earth's atmosphere, which has water and CO2. These are atmospheres that actually have rock that are in their gaseous phase that are sort of enveloping the planet. Okay. So these are simulations. There are people currently getting observations of these lava worlds, but they haven't published any of the results yet. But these are simulations of what these signatures might look like with JWST. So again, they're using the mirror instrument, it's the long wavelength instrument, and they're looking for these features right here. So silicon dioxide and silicon oxide, these are essentially the states that you expect silicate rock to turn into when they turn gaseous. And so they have these pretty easily detectable signatures of vaporized rock. And so that's really interesting thing that we can go after. Potentially more interesting is that these planets give us really the only chance to directly probe the interiors of rocky planets. We can't even do this in the solar system, right? Except for like, I guess Io, if it's like has volcanoes and stuff. But so what's happening here? So you have a rocky planet where the day side is molten, and you have convection going on in the interior. So there's convection going down the mantle back up to the surface, and it's recycling all of this material. And as that material reaches the surface, it receives all of that intense stellar radiation and it outgasses. So it turns to vapor and it shoots out into space and around the planet. So it turns out if you have a very CO2 rich interior, that CO2 is going to be detectable in the infrared with JWST. So this is a different instrument from MIRI. This is the near spec instrument, which works at slightly shorter wavelengths. And again, we have these very, very noticeable CO2 features that we can detect in emission spectra with JWST. So there are people going after these lava worlds and are looking for these features. And the reason why they want to find these features is because it could tell you something about where the planet's formed. It's believed that these, we call them volatiles, CO2 and water, we call volatiles, mostly exist in their solid phase farther away from the star. So if you find a lot of lava worlds with this, it would mean that the planets form far from the stars and then move in closer gradually versus forming directly next to the star. Yeah, go ahead.
What do you mean by CO2 interior, as in like the inner layers of the planet are actually the molten rock is composed of CO2?
Yeah, so much like sort of the icy moons of like Venus, right? There's a significant fraction of their interiors is water ice. So they actually have a plot here that has water instead of CO2, but I didn't include it. So the idea here is, yeah, these planets are forming in a region of the protoplanetary disk where CO2 and water and methane are actually not gaseous. They're so cold that they're in their solid states. And they form into a solid planet. And then at some point in the planet's evolution, it goes from very far away from the star to right next to the star. And all of that CO2 and water and et cetera that is trapped in the interior is now able to reach the surface because everything's molten and then can escape into the atmosphere and we can detect it. Does that make sense?
I think so.
Okay. Yeah. We can chat more after. Yeah, go ahead.
Is convection driven from tidal forces from the star?
It can be. So convection is essentially a mode of energy transport. Whether or not convection is going to occur is dependent on like essentially the temperature and pressure gradient inside of it. So how quickly things get cool as you move farther away from the center. And so if you have tidal forces that's heating up the center of a planet or a moon, that can lead to enough friction and heat that it drives convection. In these cases, these planets are tidally evolved enough that we sort of expect them to reach an equilibrium state where tides are not acting on the planets very strongly anymore. But we don't need tides for these planets because they get so much light from the stars that they're just hot from that alone.
I was thinking because of the radiations on the outside, there's not really greening that drives convection because the heat's already at the top, so it just doesn't recycle.
Yeah. So part of these models that you have to go into it is whether or not the planet has a molten mantle like the Earth does, right? So the Earth just has like residual heat, which is what drives convection within the Earth's mantle. So if these planets don't have that, and they're pretty much cold inside, like we think Mars is, then we might not get as much of this outgassing here. So yeah, there's a lot of variables, like you're absolutely right. And that these are like simplified models. But yeah, more things to explore. Yeah, go ahead.
Wait, sorry, just to confirm, we're still talking about like plus 2000 degrees Celsius planets, right? They're very close. Wouldn't at those temperatures CO2 and water molecules literally get break apart into like their individual elements?
So at some point, yes. I would have to double check, yeah, at what temperature they actually like photo dissociate. I don't know the answer to that off the top of my head. Yeah, I don't know. I don't have a great answer to that question. But I mean, eventually, yes, they would get so hot that the molecules themselves would break apart. Maybe the idea is that they exist for a long enough period of time where we can detect them, and then they break apart. I have to read the paper more carefully. Yeah, question.
How are we able to predict the magnetic field around these rocky planets? I mean, when you're talking about the molten mantle, convectionally flowing, because that is a bearing on whether the planet is inhabitable, at least as far as Earth's concerned, as far as can protect anything that lives there from the radiation of the star.
Yeah, that's a great question. So magnetic fields around exoplanets are something that is just sort of beginning to be explored. Right now, signatures of magnetic fields are only detectable for like Jupiter-sized planets. And so I think we'll have to get really creative in the future if we want to actually know if these rocky planets have magnetic fields at a high rate. Because right now, like, yeah, you're right, we don't know what priors we should have going into this. Yeah. Cool. Okay, so that's lava worlds. And then I wanted to plug some of my work here just because why not? So I wrote a paper about 1.5 years ago where I discovered 13 of these like potential lava worlds that we can look for with JWST. One of them I've been trying very hard to get JWST time for. Has not been accepted yet, but I'm going to keep trying until they let me use it. It's very competitive. Was that?
When are you gonna name one of these planets Mustafar?
Someone had. I saw an article when I was making this where like, I think there's a planet that has already been like colloquially named Mustafar. 55 Cancri E, if people know what that one is. 55, okay, so 55 Cancri is a cool star. It's actually visible to the eye in the night sky. It has to be somewhere very dark. You can see it, and it has like many planets around it. One of which is one of these lava worlds. So I think people call that one Mustafar. People have tried to name planets. They don't really stick. I don't know. It's fun though. Okay, so the sort of takeaway from the JWST section. Many rocky planets close into their stars may not have atmospheres at all, unless they're lava worlds, because then they outgas these rocky atmospheres. But we're going to learn more soon. There are lots of these planets that are being targeted. And yeah, all I can say is stay tuned. Look out for articles about JWST observations of rocky planets, and hopefully we'll find one with an atmosphere. That would be pretty neat. Okay, so what comes next? This is the final portion of the talk. After JWST is like long decommission. It's not a very serviceable mission. It's like very far away from the Earth. So as soon as it runs out of fuel, or if it gets hit by like enough micrometeoroids or anything like that, it's sort of done. But then we want to start thinking about what kind of mission do we want to do next? And that's where the Habitable Worlds Observatory comes in. So I'm just gonna call this HWO from now on, because that's like a mouthful. This is a concept of what one mission design might look like. They haven't fully decided on what the space telescope is actually going to look like. But so every 10 years, astronomers get together and they do something called the decadal survey, where literally, so essentially Congress and NASA, they put out like a little message and they're like, what should we spend money on to do space stuff? And astronomers come together and they write this big report. And so like, what are the biggest priorities in the next 50 years in astronomy? And one of those big priorities is to detect essentially Earth twins around sun-like stars. So this mission, whatever it's going to look like in its final form, is essentially going to be designed to find an Earth-sized planet in the habitable zone around a sun-like star and be able to study its atmosphere. So how is it going to do that? People are developing new technology now, sort of still in the works, to suppress starlight so that we can directly image planets around stars. So this is an image, this is actually a video, I'm gonna play in a second. But there's a star in the middle here. And under normal conditions, the star is so much brighter than the planets here that you wouldn't be able to see these planets at all. I think that the analogy that people make is it's like trying to detect a firefly next to a like lamppost from like on the moon or something, like really, really wild. You really need to apply some sophisticated methods to actually be able to detect these things. And so this is a video. I'll plug Jason Wong here. If people have been coming to Astronomy for long enough, they might recognize the name. Jason was a grad student here. He went and did his postdoc at Caltech, and now he's starting as a professor at Northwestern University. But Jason essentially did his PhD on directly detecting giant exoplanets. And so this is a video that he made of over 12 years of data of the HR 8799 system. So this is a star with 4 giant planets around it. And you can see, play it again, because they just continue to take data, they've actually made this video of planets orbiting another star, which is really, really impressive. But again, these are giant planets. It's easier to detect giant planets than it is to detect small planets because giant planets are bigger and so they reflect more light. But with HWO, in principle, we'll actually be able to do this for Earth-sized planets that are closer to their stars. Not only that, we'll be able to decompose the reflection of the light coming off these planets into a spectrum and be able to tell what's in their atmospheres. So this is a hypothetical reflection spectrum of a Earth twin around a sun-like star with HWO. So you'll see that we get these deep water features. And again, we got the water question. So it doesn't necessarily mean that there's life. We get some O2 features. O2 on Earth is because of life, but there are abiotic ways of forming O2. So this does not necessarily guarantee that there's life. You get CO2, et cetera, et cetera. So this is what it might look like in 50 years. I don't even know how long, after HWO is built and is in space and is taking data. But as we sort of established with some of the questions, that habitability might turn out to be a little bit more complicated. So maybe we'll find, 20 to 50 of these. Yeah, I'll let you ask a question first before I go.
So what would you have to find in the atmosphere of a planet to definitively say 100%, or at least as close as you can get, that there is definitely living creatures there?
Yeah, so that's a great question. I'll repeat it in case the video wants to hear it. So the question was, what would you have to detect in the atmosphere of a planet to definitively conclude that there is life there? And so there are a couple ideas that people go with. One of them is that you need to have a material that cannot be formed naturally, essentially, or abiotically. And so one of the things that people point to is chlorofluorocarbons. So people know about these, right? People actually talk about this. So these are the things that were emitted in like hairspray cans that were destroying the ozone layer, and that we've luckily the government has globally the governments have been like, you have to stop doing this. It's going to kill everyone.
We're assuming the aliens are also responsible for destroying their ozone layer.
Yeah, exactly. So yeah, maybe it could be indicative of past life on a planet. And so that's one thing. You can look for these things that we cannot think of any other reason that they would be in the atmosphere. Another thing that I'm sort of fond of is seasonal changes. So in the Earth's atmosphere, as the Earth goes around the sun, we get these seasonal changes in, I don't know, like CO2, et cetera. I don't really know too much about it, but things change over time in a cyclical way. And that can be indicative of life, could also be indicative of other natural processes going on. But that's another thing we could look for. There's another thing called the photosynthetic red edge, which I think is interesting. And I should have had a picture here, but I can draw one. So if you take a plot of a spectrum, this is wavelength, this is intensity. Can people see this? Where is it?
You need a better marker.
Yeah. Let's see. This one. That one's better. Okay. So this is a reflection spectrum of an Earth-like planet. And if you imagined that this planet was just like fully covered by plants that metabolize photosynthetically, you would get this pretty like low reflection in the optical, and then as soon as you hit like 1 micron, which is like just where the infrared starts essentially, you get this huge reflection. And it turns out that plants are actually, while we see them as green, they're actually extremely a lot more reflective in the infrared than they are in the green part of the spectrum. And so if you were to observe a planet that was essentially fully covered by foliage, you would get this extremely reflective signature in the infrared. And so that would be one indicator that there is life. And I don't really know of anything else that could cause that. So that's like a potentially promising thing. But then again, it goes into the question of like, well, if this life has to look exactly like how it looks on Earth, could it have gone in different directions? And maybe things don't do photosynthesis there. There are other ways that single cell, multi-cell organisms metabolize that don't require these things. So yeah, there's a lot of things to look for, is I guess the summary. That was a long answer. Yeah, go ahead.
I mean, most stars are in binary systems, are they not? I mean, that's more common. Are any of the ones that we're looking at or targeting now going around binary stars? I mean, does that materially change sort of how these things look or behave?
So most of the targets that we go after with JWST, but also with HWO in the future, are going to be single stars. But you're right. Like roughly half of sun-like stars are in binary systems, which may affect how planets form. It could affect how volatiles are like delivered to Earth-like planets. We think that water got on Earth because of comets, essentially, that bombarded it. So how does that change if you have a star that's messing up all the comets in the outer solar system? So yeah, it definitely could affect things. There are people looking at how binarity affects like how common different types of planets are. But for now, we're really selecting for single star systems just to avoid any potential complications, essentially. Another problem is that if you have a very close binary, then both stars are going to be in your observation, and you have to like subtract one out, and it gets really messy. Okay, so yeah, so habitability, it's probably more complicated than we think, and for the reasons that we said, but then I'll also highlight two here. And the first is that young Earth looked very different from what Earth looks like today. So these are showing 3 hypothetical spectra from Vicki Meadows, professor at University of Washington, of what the Earth's atmosphere would look like at various eras in Earth's history. So in the purple, we have the Archean age. This was pre-life, so this is essentially Earth in its like most primordial form after everything cooled and like oceans formed. Then in the, I don't know, greenish and bluish, we have the Proterozoic. So Proterozoic is when oxidation happens, so life essentially formed. Things, plants, cells, etc., started metabolizing CO2 into O2. And then we have the modern age, which there's life now too. And so we can see in this figure that if we were looking at our Archean Earth analog, we would essentially see no oxygen, which, yeah, go ahead.
Well, why the heck is there that much ozone? Like what?
Yeah, well, okay, so I'll get to that in a second. But so in the Archean age, there was not a lot of oxygen on Earth, because the oxygen on Earth was formed by life, was metabolized by plants. So if we observed an Earth twin that is in its Archean analog stage, we might conclude that, well, this is not a habitable planet, or like this, might never have a habitable atmosphere, etc. But that's not necessarily true, right? Because life takes time to form. And so the point of this is just saying that we have to consider planets along the time axis too here. Just because a planet does not have life as we're looking at it, doesn't mean that it never had life, and it doesn't mean that it never will have life in the future. We might just be catching it at a time where there is no life. So coming back to your question, why is there so much ozone? So ozone forms, you might know this, ozone forms via photochemical reactions in the sort of various levels of the atmosphere, but it starts with O2, and then they essentially break apart, and then I think free, like single atom oxygen can merge really easily with O2, and then it forms ozone. Yeah, there's this whole ozone cycle, which is part of why the ozone layer is important. I guess going back to the chlorofluorocarbons, the reason why those were bad is because it essentially stopped this reaction from happening where O2 turns into ozone, which is why we needed to stop producing those chemicals, because we weren't producing any ozone. So yeah, so early Earth didn't look like it was habitable, but it doesn't mean that it's not a quote unquote habitable planet. And then, you know, same thing for Mars, but the opposite. So Mars, we think billions of years ago, could have had liquid water oceans, could have potentially had life that we just haven't sort of detected the remnants of yet. And so if we were to find something like Mars today as an exoplanet, you know, we shouldn't jump to the conclusion that, well, that's like a dead world, that's not inhabitable, because at one point it may have been. And we may never know that. And so that's another reason why it's very important to get a sort of large sample of these planets so that we can approach this from a statistical level and really get down to the good questions. Yeah, go ahead.
Big ozone spike, was that right after the evolution of phytoplankton? So there was a whole bunch of more oxygen in the atmosphere before other organisms of bacteria had evolved to reverse the process, basically?
Possibly. I don't know. Yeah, I have to read this paper again. I don't remember exactly why that features there. But if you, I'm sure people in here know more biology than I do. So yeah, that may be a possibility. Okay, so leave us with our last takeaway here. So with HWO, we will probably determine how common habitable Earth-like planets are in the galaxy through direct imaging of Earth analogs. And that's actually all I have. So I will leave you with that, hopefully optimistic note, and I can take more questions if people have more questions.